Hello and welcome to this video on the ICND2 series. In this video, we're going to be looking at frame relay. So we're going to look at frame relay concepts. We're also going to examine some terminologies that are used in frame relay. And finally, we're going to look at frame relay design options. So let's get started. So what is frame relay? The first thing you need to know about frame relay is the fact that frame relay is a packet switched network technology. And if you remember from a previous video, when you have a packet switch network, when you're trying to send data, you can divide data into smaller chunks called packets, and these packets are sent across the service provider network. And then on the other side, they're assembled together to make meaningful information. So that's how a packet switch network works. Now for frame relay, we use what's called permanent virtual circuits. And the permanent virtual circuit is just a logical connection between two devices or two locations. So for instance, we have this frame relay network here. Normally, if you want connectivity between R1 and R2, you're going to play a service provider for connectivity between R1 and R2. And it's going to give you a permanent virtual connection between R1 and R2. So you have a virtual circuit between R1 and R2. And it's going to be permanent in the sense that it's not to turn up and turn down like the way we have in circuit switch networks. So unless they stop paying for the connection, that virtual circuit will always be there. Similarly, you can say you want to connect R2 to R3, R3 to R1, it's going to give you a permanent virtual circuit. So typically in frame relay, you enter a contract with a service provider and gives you a PVC with some particular characteristic, which we'll talk about in a second. Now, these PVCs are identified using what's called DLCs. And DLC stands for Data Link Connection Identifiers. Now, obviously, the name, you can guess that DLCs are used as a data link layer. So in frame relay, DLCs are actually the layer 2 addressing. So the way we have the MAC addresses in the Ethernet, we actually have DLCs in frame relay. And how DLCs work? DLCs are used to identify the permanent virtual circuit. So in this case, if R1 has a PVC to R2 and there's another PVC to R3, what's going to happen is that R1 is going to have a DLC for connection between R1 and R2, another DLC for the connection between R1 and R3. So let's say the DLC for R1 to R2 is 102, and the DLC for R1 to R3 is 103. Now, based on this DLCs, it's going to tell me how to send traffic across the network. Now, assuming we have only one interface, and we have the two DLCs on the same interface, we have to be able to find a way to resolve DLCs to the right IP address. So for instance, let's say we have 192.168.1.0 as our network here. So R1 is the 1.1, R2 is the 1.2, and R3 is the 1.3. Now R1 has to find a way to know that when you need to send traffic to 192.168.1.2, it's going to send it through the DLC 102. While if you want to send packets to 192.168.1.3, you're going to send it through DLC 103. Now, think of the DLCs like doors. So you have these tunnels over a service provider network, and you don't know what's going on inside the service provider network, but on your network you have a door, and a door is identified by a DLC. Now you know that if you send something out through the right door, it's going to get to the right place. But if we send this packet to the wrong door, it's going to get to the wrong place. So what we need to do is to make sure that we're always sending out those packets through the DLC, which is the door 102, and we're sending R3's packets to the DLC 103, and everything's going to be fine. So DLCs are locally significant. What this really means is that DLCs only have to be unique on a particular router, in the sense that you can have DLC 102 and 103 on R1, and also have DLC 102 and 102 on R2, and it really doesn't matter. Again, think of it like doors. So if we have doors at a particular location, let's say this is London, so you have door 1, 2, and 3 on London. We can also go to New York and still have door 1, 2, and 3. So in that case, we know that door 1 in London takes it to New York. Or in this case, door 102 in London takes you to New York. Once you send something out door 102, it's definitely going to get to New York. But at the other end, you may have a different door number. It may have the same door number. It really doesn't matter. As long as when New York is trying to send traffic to London, it's also using the correct door. Everything's going to work fine. Now in the lab environment, always try to use router numbers to create the DLC numbers. So for instance, if you want to go from router 1 to router 2, I have DLC 102. I'm going from router 2 to router 1, I have DLC 201. The trick is that it really doesn't matter what the number of DLC is, as long as the DLCs are locally unique. On the particular router, you can have two DLC 102s. Besides that, you can have any number of DLC, and it's going to be fine. If you have more than one DLC on a particular physical interface, they have to be able to resolve DLCs to the IP addresses in the sense that if you have just one interface, let's say serial 0/0, you have DLCs 102 and 103, you have to be able to know that DLC 102 ties to 192.168.1.2, while DLC 103 ties to 192.168.1.3. And you can do that either automatically or statically. So by default, in every frame rate interface, we have what's called an inverse ARP, which is turned on. And the name's really intuitive because remember we use ARP, the address resolution protocol, to resolve the layer 3 IP addresses to layer 2 MAC addresses. But with the inverse ARP, we actually have our layer 2 DLCs, and I want to resolve this through the IP address. So we actually know the DLCs, but we don't know what the IP addresses are at the other end of the DLC. So we want to resolve the IP addresses, and that's why it's called inverse ARP. So automatically inverse ARP is turned on. Now, the second way to do that is to use the static method in the sense that sometimes we actually need to go inside the router and teach it about a particular IP address. And the way to do that is we're using what's called a frame relay map. So you have a command that's called a frame relay map. And this command allows you to statically define IP addresses and tie them to the DLCs. Now, we're going to go into this more in detail when we configure frame relay, but for now, that's what you need to know about frame relay. It uses permanent virtual circuits, and the PVCs are identified using DLCs. So let's examine some more frame rate terminologies. And the first one we're going to look at is what's called the LMI. And the LMI stands for Local Management Interface, and it's just the standard for communicating between the router and the frame relay switch. So in the sense that we have a frame relay cloud, we have router 1, and it's connected to the frame relay cloud. What really happens is that router 1 is connected to a frame relay switch. So this is a frame relay switch that's connected to router 1. Now there need to be communication between router 1 and the frame relay switch, and that's handled by LMI. So LMI was just a standard that was created. Now, over the years, we have three different standards. We have the ANSI standard, what's called Annex D. We also have the Cisco standard, and we have the Q933A, or what's called Annex A. And that was by the International Telecommunication Union, the ITU. Now, these are the three LMI types which you need to know for the ICND2 exam. Well, the good thing is that LMIs are negotiated automatically by Cisco device, so you don't need to manually go into the device and configure the LMI because the Cisco routers can automatically detect which LMI to use, and everything is done automatically for you. Now, the next thing is frame rate bandwidth technology. So, for instance, if we set up frame relay between two sites, let's say router 1 here connects to the frame relay cloud, and it has a PVC that goes to router 2. Now, whenever you buy a link from the service provider, they actually sign what's called an SLA. And the SLA stands for Service Level Agreement. It's just an agreement that shows that the contract that you have with a service provider, the kind of link that you're going to get and things like that. Now, some of the technologies that you might find in the SLA would be things like the committed information rate. And the committed information rate is just the guaranteed bandwidth on this PVC. So for instance, if you're buying a PVC that has a CIR of 5 Mbps. What this really means is that the link is going to be 5 megabits per second guaranteed. Now, it could go beyond 5 megabits per second, and that's what's called the burst. So sometimes it can actually burst above the guaranteed information rate, which is a CIR, and gets to a burst rate. So you can actually have a link that has a 5 Mbps CIR, and then the burst rate goes to 20 Mbps. So what the service provider is trying to tell you is that since the network is being used by many customers, at every point in time, if you need to send traffic, I guarantee that you're going to get 5 megabits per second. But if other customers are not sending enough traffic, then you can go as high as 20 megabits per second. But at no point will you time where you go below 5 megabits per second. So it always seems like a good deal because you think you're paying for 5 megabits per second, but you get up to 20 megabits per second. But trust me, the service provider has totally figured it out. And while they're giving you great value for money, they're also not losing on their end. Now, the local access rate is just the speed of the device or the speed of the media in the sense that you can have a serial connection that can run 54 megabits per second. Now, the mere fact that it can run 54 megabits per second does not mean that the link between router 1 and router 2 is going to be 54 megabits. It's actually going to be 5 megabits, but local access rate just identifies the speed of the cables and the physical connections of the network. So that's like the maximum that you can ever get to. Because even if you buy, for instance, 150 megabits per second from a service provider, if you're using cables that only support 54 megabits per second, then your 155 megabits would totally be wasted. So you need to be familiar with what your local access rate is, but it's usually way higher than your committed information rate. Now let's move on to the interesting part, actually designing frame relay networks. And we're just going to look at two kinds of networks in frame relay. And the two kinds of networks we're going to look at are the fully meshed network and the hub and spoke network. So from the names of the design, a fully meshed design is a design where everybody has connectivity to everybody. So for instance, in this case, we have router 1 that's connected to router 2 and router 3. Router 3 is also connected to router 1 and router 2, and router 3 is connected to router 2. So you have a full mesh, and all the devices can send messages directly to the other device without going through another device. And so that's the fully meshed design. But of course, we know that a fully meshed design is usually very expensive because now you have 3 sites and it looks like, okay, we just need 3 PVCs. But if we had 10 sites and everybody has to talk to everybody, we're going to have it into n minus 1 over 2 PVC. So if you have 10 sites, we're going to have 10 times 9 over 2. So we're going to have 45 PVCs, which is actually a lot of PVCs because you're going to pay per PVC. And that makes it really expensive. And most large networks don't even have 10 sites. They have upward of 20 and 50, 100 sites. So you can imagine for a network with 100 sites, you're going to need thousands of PVCs to have a fully meshed network. That really doesn't make any sense. So the other design option to have is the hub and spoke design. And in this case, what happens is a hub is selected. Router 1 is our hub. And then the remaining sites on the remaining devices are just spokes. So this is a spoke. And this is also a spoke. So the only PVCs we need are the ones between the hub and spokes. So you have a PVC from the hub to the spoke. If you have a spoke that's introduced, say router 4, they're just going to have another PVC to the hub, and that's it. So what happens is that everybody has to send stuff to the hub before it gets to the spoke. Now, of course, this would increase the latency in the sense that if router 2 wants to send stuff to router 3, it first has to send it to router 1, but then to router 3. But it's fine, except in cases where you have really slow links and if you have dealing with like voice over IP. But usually the hub and spoke design works very well, where every spoke has just one connectivity to the hub. Now, for the frame relay interface types, we actually have the physical interface, which is like a serial interface. Router 1 is connected via serial link to the frame relay cloud. Router 2 is also connected via serial link to the frame relay cloud. And router 3 is also connected via serial link to the frame relay cloud. Now, normally we can use this physical interfaces in which set a frame relay and everything's going to work fine. But in that case, what's going to happen is that we have a point to multi-point network here. So because router 1 has 2 PVCs, but it's using only one interface, that interface is going to be a multi-point interface. And because they're a multi-point interface, they have to figure out the DLC resolutions for that interface. Now for point-to-point interfaces, you really don't need to figure out any DLCs for resolution because there's only one DLC anyway. Now the other thing you need to know about this kind of network is that when you have multi-point interfaces, is that everybody's on the same subnet. So you can have like 192.168.1.0/24. And this is going to be .1, .2, .3, .4. And you get the picture. And so even if you have many sites, all the sites are going to be on one network. And what that really means is that because they're on the same layer 3 subnet, for everyone to communicate with each other, they have to figure out the layer 2 connectivity. And so for R2 to communicate with R3, for instance, R2 has to figure out a DLC to reach R3. And if you have not configured R2 explicitly as a point-to-point sub-interface, which we'll talk about in a second, then R2 will need a frame relay map for R3's IP address. And it can get really messy. Now, aside the physical interface, we also have sub-interfaces. I'm just going to clear the screen in a second. So we have a Also have subinterfaces that can be used in frame relay, and we have two types of subinterfaces. So when you go under the physical interface and, for instance, say interface serial 0/0, you can say encapsulation to be frame relay. You can create a subinterface and say interface serial 0/0.1, for instance. And at that point, you have to specify whether it's going to be a point-to-point subinterface or a multi-point subinterface. Now, for instance, if you are creating a subinterface on R1 and we still want to maintain a multi-point network, what we're going to do is that we're going to create a multi-point subinterface. So we can say that this is serial 0/0.1, and this is a point-to-point subinterface. And then we can create subinterfaces here and say serial 0/0.1, and it's point-to-point. And this is also serial 0/0, and it's a point-to-point. Now, if we do that, all the issues that we had before are still going to be the same in the sense that we still have a multi-point interface, and we still have to figure out the layer 2 connectivity between these multi-point interfaces. But with spokes, if you're using a point-to-point subinterface, we don't need any frame relay map connectivity to define router 3's IP address, for instance, because it's just going to know that it has the one DLC, and whatever traffic it needs to send by frame relays is just going to go through that DLC. So think of it like you just have one door. You don't have any other choice. You need to get out of your network. You have to use that door. So that's how point-to-point subinterfaces help us to do. We can now define one DLC and tie it to a point-to-point subinterface, and all traffic that's going through that point-to-point subinterface is going to go through that DLC. Now we can have a scenario where we actually split the interface of R1. So instead of having one point-to-multi-point subinterface, we can have two point-to-point subinterfaces. So we can have serial 0/0.1, a point-to-point subinterface, and then serial 0/0.2 and another point-to-point subinterface. So technically, we have two interfaces at R1, even though they're sharing one physical interface. At that point, we can use two different subnets. So here we can use the 192.168, the 1.0/24 network, and here we can use the 192.168 2.0/24 network. So with these design options, we're actually splitting the frame relay network into two networks instead of having one shared network with a multi-point interface. Now, which one is better? It totally depends, but I recommend using point-to-point subinterface because it takes care of a lot of problems. So, for instance, one issue you can face with point-to-multi-point subinterface is split arising where you're using a routing protocol. I'll just clear the screen again. So let's assume we're running a distance vector routing protocol, for instance, RIP version 2 or EIGRP, and we're running it across a frame relay network. If this is a multi-point interface, that means that the updates that are sent from R2 will go to R1, and then the updates need to be sent to R3. But if you remember our loop prevention mechanism in distance vector routing protocols, we have what's called split horizon. And the split horizon rule says that updates received via an interface cannot be sent out to that same interface. So if a multi-point interface, what that means is that you're going to get updates from R2, get into R1, but they're not going to be able to go to R3. That's because split horizon is turned on. And so if you're using a point-to-multi-point network, you actually have to go in under the interface and disable split horizon. And if we disable split horizon, you know that you can have loops. And you have to trust that the other loop prevention mechanism would prevent loops on the network. So to keep things simple, you better just use point-to-point networks and use different subnets for different PVCs. So technically, those are design options that you have. You can have a fully mesh design, you can have a hub and spoke design, and whether you're using fully meshed or hub and spoke, you can actually have point-to-point subinterfaces or point-to-multi-point subinterfaces or physical interfaces, and all of them work in theory if you configure them right. But my preferred option is the point-to-point subinterface. Now, we're going to explore all these configuration options when we configure frame relay in the next video. So in this video, we looked at frame relay concepts. We also looked at some frame relay terminologies. And finally, we looked at design options that we needed for frame relay. Thank you very much for watching.